Hello, everyone. It's a pleasure to have Tao Jiang as our speaker today. He'll talk on Turán exponents of graphs. As usual, if you have questions during the talk, please write it in the chat. Otherwise, we'll have question time at the end of the talk. And also we'll have some informal discussion after that, which won't be recorded. So Tao, you can start.
Okay, thanks Liana for the invitation and introduction. Thanks also to the other organizers for having me. So today I would like to talk about Turán exponents of graphs. I'm not familiar with chatting with the chat section very often. So if someone asks a question, I don't see the question, maybe Liana can remind me. So don't hesitate to ask any questions in the process. So to start, everyone is familiar with the so-called Turán number, but just to be safe, let me remind you the definition of a Turán number. So suppose I give you a family of graphs. I define the Turán number, or sometimes it's called extremal number of f, to be, sorry, I'm missing a maximum here. So the maximum number of edges among all n-vertex graphs, which does not contain any member of the family F as a subgraph. So when such a graph G does not contain any member of the family F, I'm going to say G is F3. So we want to maximize number of edges among F3 graphs. So you're all aware of this classic theorem of Mantel in 1907, who determined the Turán number for the triangle. So it's roughly n squared over 4. And we all know the extremal construction is to take the complete bipartite graph, the balanced complete bipartite graph. So now more generally, there is this really nice theorem due to Erdős, which was later observed by Simonovits as well, that actually determines the Turán number of any family of graphs of non-bipartite graphs. So more specifically, if P denotes the minimum chromatic number among all members of F, and if this P is at least 3, then the Turán number for the family F is going to be asymptotic to 1 minus 1 over P minus 1 times n choose 2. So it's really a very nice theorem in many ways. First, it determines the asymptotics, and second, the answer's dependence mainly on the chromatic number, a very simple parameter, and it doesn't rely that much on the particular structure of the graphs F. However, on the other hand, when P is 2, much less is known. So it's like a direct, strong contrast to the P at least 3 case. Okay, so I would like to give some philosophical view of why the P at least 3 case is more manageable. Even though what I'm going to talk about in the next few minutes are probably familiar to everyone, but I still want to put some kind of philosophical perspective on it. So one reason the non-bipartite case is more manageable is that there's a very simple universal lower bound. Namely, you just take the P minus 1 partite Turán graph, by which I mean the complete P minus 1 partite graph with all the parts having about the same size. And so if your family F satisfies that the smallest chromatic number among the members is at least P and P, then you can see that this Turán graph, this P minus 1 partite Turán graph is automatically going to be F3. The reason is every subgraph you can find in this Turán graph is already P minus 1 partite or P minus 1 colorable. So it's not going to give you any member of F. So a simple calculation shows that this number of edges in the Turán graph is roughly this 1 minus 1 over P minus 1 times n choose 2. So that provides the lower bound. Again, the nice thing here is that this lower bound solely depends on the chromatic number of F. And luckily, a matching upper bound is not that hard to prove. There are many different proofs. Here, I would like to point out, to me, a more natural proof is to use the supersaturation of KPs. So namely, if you have an n-vertex graph that has just slightly more edges than the p-1 partite Turán graph, okay, so you have this plus epsilon fraction more. Then just by simple counting, you can show that there are omega n to the p copies of Kp. So you have a constant proportion of all the possible p sets inducing a Kp. So now if you just define auxiliary p uniform hypergraph H, whose hyperedges are precisely those p sets that induce Kp's, then this p graph has n vertices, but has at least some epsilon n to the p edges. So it has positive density. Then by a classical result of Erdős, if you have positive density, you can find a large complete p-partite p graph as a subgraph. So now translate back into G, what that means is that G contains a large blow-up KPT, by which I mean blow up each vertex into T vertices, replacing each edge with the complete KTT. So G contains T blow up of KP, and if you make T large enough, it's going to contain any bounded size P chromatic graph. So you can find a member F. So you see both the lower and upper bounds are quite simple. So we're lucky. Okay, moving on to the bipartite case. Why are they difficult to determine? Again, it's just my philosophical viewpoint. First, good lower bounds are very hard to obtain. And unlike the non-bipartite case, lower bounds for the bipartite case are much more reliant on the specific structure of the forbidden F. So for instance, if you want to forbid even cycle versus complete bipartite graph, the information you need to use is very different, and the construction likewise is very different. So if you use a simple random argument, it usually doesn't give you a very good bound. Essentially, all the good lower bounds are algebraic in nature. Also, good upper bounds are hard to find too. So earlier in the non-bipartite case, I give you a simple counting argument using supersaturation of Kp. But here, you may try to count some substructures, but there's some difficulties. One is it's not quite clear what the correct substructures to count. And second, even if you have enough of them, it's still not easy to force F. So the arguments, again, become very specific to the structure of F. So I think the essential issue is that we're dealing with host graphs which in a very sparse range, right, with number of edges subquadratic. So one cannot typically expect too much uniformness. So that's the overall picture. In fact, until recently, for very, very few bipartite graphs F, do we actually know the order of magnitude? Right? So unknown even for order of magnitude. For essentially all F. Okay. Okay. Now, but let's get more into it. So every discussion on bipartite Turán problem would have to mention this Quevery-Soch-Turán theorem, which provides upper bound on the extremal number for KST, the complete bipartite graph. So if S is the smaller part, then the Turán number is bounded by big O of n to the 2 minus 1 over S. Now the proof is very simple. I believe everyone in the audience knows the proof. But again, I want to kind of reiterate it because similar flavor of argument would appear later. So the idea is your average degree is roughly n to the 1 minus 1 over s. So if you count number of s stars in your graph using convexity, you should have at least n times d to the s many. So if you plug in d equals roughly n to the 1 minus 1 over s, you get n to the s. So you have omega n to the s many k1s. Well, here by omega, I really mean some large constant c times n to the s many, because you are free to adjust your coefficient. Or maybe I should call this c prime. You can play with this capital C earlier, so now you can make c prime large. So then if you think about this many k1s, there's only n choose as many ways to choose S set as a leaf set. So by pigeonhole principle, you can get many of them sharing the same leaf set. Okay. So you have lots of K1S sharing the same leaf set. So that creates KTS. Again, I repeat the simple argument because later we'll see something more general. Now, this is only upper bound. It's not known whether it's tight for every T and S. So I didn't list all the results. It's known to be tight for S equal 2 and ST equal 3. But I want to just mention two general results in terms of the lower bound. The first one is due to Kola, Ranier, Zaber, who show that this exponent is indeed tight when T is at least S factorial plus 1. This was slightly improved later by Alon, Ranier, and Zaber to show that exponent is correct when T is at least S minus 1 factorial plus 1. Relatively recently, Blagojevich, Bukh and Karasev, and Bukh give an alternative proof of this fact when T is sufficiently larger than S. Now, the significance of this their argument is that, so their T is not that optimal, but the significance is that it actually introduced a new method which later extends to a much more general lower bound for much larger family of graphs. So this is so-called random algebraic method that they introduced. So in their work, the basic idea is not to construct the graph just using random graph, but rather take a random polynomial and then define a bipartite graph correspondingly. And then they apply some tools from algebraic geometry. So I won't get into details, but this method turns out to be very promising, and it was subsequently found significant applications. So first, Conlon used this method to show that for all k at least 2 and sufficiently large L compared to k, the Turán number for theta KL is lower bounded by n to the 1 plus 1 over k. Okay, so let me remind the audience what the theta graph is. So theta KL is the graph you get by taking L many k paths sharing the same ends, but otherwise disjoint in the middle. Okay, so each path has the length k. So you may recognize that if L many, you may recognize that if L is 2, you simply get C2k, right? And you may recognize this exponent 1 plus 1 over k is an upper bound for C2k. And it was a long standing conjecture of Erdős and Simonovits that for C2K, the Turán should also be lower bounded by n to the 1 plus 1 over k. But that's still open except for k equals 2, 3, and 5. So I think part of the motivation for studying Theta graph is it's sort of motivated by the even cycle problem. And indeed, Conlon was able to show that if you have many k paths between x, y, instead of having just 2, then n to the 1 plus 1 over k indeed is the correct lower bound. So I didn't mention here in the slide, but I should mention that there's also a very nice result by Jacques Vesterati and Jason Williford, who show that for k equals 4, when L is 3, you already get the correct exponent. So they don't quite establish the conjecture, the lower bound for C8, but they're able to do it for theta 3, 4. They showed it's lower bounded by n to the 5/4. Okay, it's Vesterati and Williford. Okay, so going back to Conlon's result, it matches an early upper bound due to Faudry and Simonovits, who showed that for k and every L, the Turán number for theta KL is upper bounded by n to the 1 plus 1 over k. So that gives you the exact order magnitude for theta graphs when L is large. Okay, so this is one application. But soon after, Bukh and Conlon together develop a very general lower bound that's kind of motivated by this KST and the theta. So what they observed is, if you look at KST, you can think of KST as taking S star and taking T many copies of S star, sharing the same leaf set. If you think about the theta graph, you can think about this as taking a P path, a K path, then take many of them, sharing the same set of leaves. Okay, and here, when I say sharing the same set of leaves, I do insist that outside the leaves, they are internally disjoint. So they observe that, well, maybe something more general is true. Maybe you can do this kind of operation to every reasonable tree and get corresponding bipartite graph for which we can say a lot. Indeed, that's their results. So to discuss the results, I need to introduce some terminology. So suppose I give you a tree with B edges and A non-leaves. I'm going to define this parameter rho to be B over A. So you can think of this B over A as the number that tells you if you delete all the non-leaves, how many edges do you lose per vertex? You lose B over A edges per vertex. Okay, so think of this parameter in this way. And now I'm going to say T is balanced if for every possible subset of non-leaves, when I delete them, the number of edges I lose per vertex is at least as large as rho. So in other words, for every subset S of non-leaves, the number of edges in the tree T that contains a vertex in S is at least rho times the size of S. So if this condition is met, then I'm going to say T is balanced. Okay, so here I give you some examples of balanced trees and unbalanced trees. So on the left, I drew a star. You can show a star is balanced. And I drew a path, and you can show that you can verify that a path is also balanced. On the right, I draw this little tree, and I can check it's actually not balanced. Okay, and the reason is this. So you look at the leaves and look at the non-leaves. So there are 3 non-leaves, and there are 5 edges. So rho is 5/3. But now, if I look at the circled subset S of non-leaves, there are 3 edges incident to it. So row of S, which is number of edges incident to S divided by S, is 3/2. So 3/2 is 1.5, is less than 1.67. So this row of S is not at least as large as row. So this is an unbalanced tree. Okay. So this is a notion of balanced, and this condition actually plays a role, an important role, both in the lower bound argument and in the upper bound conjecture. So now, such notion may be limited if the kind of role you can achieve by balanced trees is limited, but it turns out that's not the case. So Bukh and Conlon show that for all integer pairs A, B with A at least 1 less than B, you can find, you can construct a balanced caterpillar TAB, whose row is exactly B over A. Okay, so you can realize every possible B over A, essentially. And this caterpillar is quite natural, so I won't get into details, but if you read that paper, you can see it's a simple construction. Okay, so the significance of this is they are going to generalize the KST and Theta graph by taking a balanced tree, many copies of the same balanced tree, and glue them at the leaves. Okay, so this is their main result. So let T be a balanced tree with B edges and A non-leaves. Define rho to be B over A. Let R be the set of leaves. Then, for sufficiently large L, they can show that the extremal number for this family script T raised to L is lower bounded by n to the 2 minus 1 over rho, which is n to the 2 minus A over B. Okay, so let me explain what this family T to the L is. So I already touched upon that earlier. So let's say here is my T, it's balanced. So I look at the leaves. And now I'm going to just take L copies of these T, but make sure that each copy agree in the leaves. Okay. So here I only drew 2 copies, but you can do as many copies as you want. Now the one I draw here is clean. In general, they only want L copies of T agreeing on the leaves, but they don't care whether outside the leaves these copies overlap or not. So it's a family. But to avoid this family, already they are running an algebraic approach would already establish this lower bound. Okay, from this point on, our focus will be on a clean copy, a clean member of this family. By clean, I mean that these copies of T, they agree on the leaves, but are otherwise vertex disjoint outside the leaves, such as the one I drew here, okay, with 2 copies, but you can repeat this L times. So I'm going to denote this special member, the clean gluing, by just the regular T to the L, okay? So as example, if I take the K path and do the clean gluing of the K path, then I get a Theta graph. Okay, so this lower bound is really, right. So the lower bound is really nice in that it immediately generalizes the earlier argument lower bound for KST and for Theta KL. So you can check. I won't go into too many details, but I already said that stars are balanced. So if you take T's power of K1S, you get KTS. And I also said the K path is balanced. If you take L power of the K path, you get a Theta KL. And if you compute the density rho for the trees and look at exponent conjecture indicated by the construction, it's exactly what we had before. But the Bukh Conlon lower bound is much more general. It works for every balanced tree. Okay. What's nice?
Can I have one question?
Mm-hmm. Yeah.
About Theta Graph, the result of David, does he also prove this for all L much larger than K, or his result is for Theta Graph?
For Theta Graph, yes. For L much larger than K, yes.
His original result is also for that range?
Yes.
When L is much larger than K?
Yes, yes. As I mentioned, that the random algebra method, it's hard to control the threshold on how large L is. It's quite large. So as I mentioned earlier, that for the even cycle problem, your L is 2, right? And the conjecture is that n to the 1 plus 1 over k is the correct exponent. And for k equals 4, there's this result of Strati and Williford, who show 3 paths is enough to force this lower bound. But in general, it's a different set of problems one can look into. Okay, but also it's nice that there is a quite very easy matching upper bound. So if you want to force the family script t to the L, you want to say it's also upper bounded by big O of n to the 2 minus a over b, then you just count number of copies of this tree T, much like in the Cavalier-Soch-Turán theorem. If you just do the simple counting, you can show that once your graph has number of edges little omega, by which I mean growing faster than n to the 1, you can think of this as any large enough constant times n to the 2 minus a over b, then you can find omega n to the b minus a plus 1 copies of t, just by simply greedily grow your t from any vertex. Then, because there are only n choose b minus a plus 1, well, maybe we're looking at labeled leaves, so maybe a safer way to say this is there's only n to the b minus a plus 1 ways to pick your set of leaves labeled. Then you can get omega 1 of these copies of t agree on the leaf set, right? So so this is your t, you get many copies of this t. Okay, but here, when you say you have many copies of the t agreeing on the leaves, you actually have no control on how they overlap outside. So they make laps, creating some degenerate copies. So this argument is only good for forcing some member of the family. Okay, so again, it tells you that once your graph has c times n to the 2 minus a over b edges, you are guaranteed to get some copy from this family, because you know there are enough copies of t grew at the same leaves. But unfortunately, as I said, this simple counting argument cannot force any one particular member of the family, no matter which one. Maybe not which one, but for any favorite member you pick, you can say I definitely get this member. Because again, this counting only tells you how many copies are glued at the leaves. It doesn't tell you their intersection structure outside. Okay, so what's next? Well, okay, here is just summarizing that the lower bound of Bukh and Conlon is the main breakthrough, but unfortunately for them, for the family script t to the L, there's a very easy upper bound. So significantly, this implies that for every rational number a over b between 0 and 1, there exists a family of graphs script f whose Turán is on the order of magnitude of n to the 2 minus a over b. Okay, because earlier I said for every such a b, you can find a balanced caterpillar with the desired row value. So this is quite significant, because it tells you every rational number between 1 and 2 can be realized as exponents for some family of bipartite graphs. So this answers one form of a long-standing conjecture of Erdős and Simonovits, which were reiterated by Franco, and then also in the survey by Zoltan and Mickey. Okay, so what's next? The next goal is to look at the Bukh-Conlon theorem and ask, can you replace this family F with a single graph F? Okay. So it's true that for every rational R in the interval from 1 to 2, you can find one single bipartite graph F whose Turán number is theta of n to the R. This question was credited to Erdős and Simonovits, though their original conjecture was written in even stronger forms. So if you remember the discussion about the Bukh-Conlon lower bound construction, it forbids every member of the family to appear. So in particular, if you single out any particular member, it also works, right? It's also a lower bound. So we just need a matching upper bound. Now, in the Bukh-Conlon case, the upper bound is very straightforward. But if we want to force one particular member F, then it becomes much, much more difficult. And in fact, that's what they conjectured. So they conjectured that if T is a balanced tree with B edges and A non-leaves, then for all integers, positive integer L, the extremal number for this regular T to the L is upper bounded by big O of n to the 2 minus A over B. Okay. Yes, this comment just says that if the conjecture holds, then that would answer the question for the existence of single F. Okay. But having worked on this problem for a while, let me philosophically say that this conjecture is much stronger than what's needed for the rational exponent conjecture. Yes, so it's actually quite difficult. Okay, so what was known prior to the Bukh-Conlon's work? Okay, when I say what was known, I'm not talking about what's known relative to the Bukh-Conlon conjecture, but what's known about exponent. So prior to their work, very limited exponents are known. So one kind is 2 minus 1 over s, realized by complete bipartite graphs. Another kind is 1 plus 1 over k, realized by the theta kl. Okay, and for all the other exponents, prior to their work, it's not known whether there is a single graph whose Turán is on order magnitude of n raised to that exponent. Okay, but a lot has changed since then. So let me mention some recent progress for the remaining time. So first in 2 years ago with Jie and Liana, we established a new sequence of exponent, one of the form 2 minus 2 over 2s plus 1. Okay, so again, in the previous slide, I said you can realize 2 minus 1 over s, you can realize 1 plus 1 over k, but this 2 minus 2 over 2s plus 1 is not one of them. Okay. And also there we can show there's a f with exponent 7/5. Okay, now I spent a lot of time discussing the Bukh-Conlon conjecture, which is about the Turán of the L's power of the L's rooted power of a balanced tree. But in our results, the f we find, the main f we find for this sequence is not really coming from the rooted power of a balanced tree. It's more motivated by the result of Erdős and Simonovits on the cube graph. So the cube graph is the one I drew on the left. They show that the Turán for the cube graph is big O of n to the 8/5. So then one way you can think about, okay, I won't say too much about this, but so the graph we showed has this desired exponent is so-called, we call this HST, which is obtained by taking a S matching on the left, taking a T matching on the right. And if you view them as bipartite graphs with parts X and Y, and then you join this S matching intersect X completely to the T matching intersect Y and the other direction as well, diagonally. Join them by complete bipartite graphs. So if S and T are both 2, you can see that this H22, maybe it's not quite accurate to say this H22. H22 will contain the cube, okay? It contains the cube, I think, plus the diagonal. But anyway, so, right, so we show this. So in particular, if our T is large enough, then for H2T, we also get a big O of n to the 8/5, okay? Which is, will be theta n to the 8/5 if T is large enough. Soon afterwards, a few months later, Kam, Kim, and Liu also had some nice results. They show that for all integers a, b, at least 1 with b bigger than a, and b congruent to either plus or minus 1 mod a, there is a single graph f whose Turán is theta of n to the 2 minus a over b. Also, there is a graph with exponent 10/7. Okay. So the condition is phrased this way, right? It looks somewhat unintuitive where it comes from. So let me explain what this condition comes from. Namely, the results have two parts. The B congruent to -1 mod A part is that established by verifying the Bukh-Conlon conjecture for the following special tree. Okay. Again, Bukh-Conlon conjecture says if you take the clean else rooted power of balance T, then it should be n to the 2 minus 1 over rho of T. So they verified this for this tree. So this, I should say, family of trees, because you can change the parameter S and T. So it's just, you can think of this as you start with T star. So you have a central vertex with T children, and then you're going to add S leaves to each vertex. So it may look a little bit unintuitive why the number of leaves you add to the central vertex also has to be S. This is because of the particular argument they use to establish upper bound. So they use dependent random choice. So it's crucial that this number S matches the other numbers here. So later you can see that these problems, they are not so easy. If you change this S to something else, the problem becomes difficult, but very different, because the row value also changes. And their B congruent to 1 mod A result follows from applying their B congruent to -1 mod A result, applying the following densification lemma to the earlier result. So what's the densification lemma? It's quite nice. It's very nice. It says, if you know 2 minus A over B is realizable, then so is 2 minus A over A plus B. Okay, so that gives you a way to generate many new exponents, because you can iterate this process, right? Now, this lemma actually follows quite quickly from a classic reduction lemma of Erdős and Simonovits. But I won't get into that. You can look it up. But it's very nice for them to see the connection between the Erdős-Simonovits reduction lemma and the exponent problem. Okay, and then soon after that, Conlon, Yancey, and Li find more exponents. So they're able to realize n to the 1 plus s over sk plus 1 for all integer pairs sk at least 1. And this also confirms the conjecture of Kam, Kim, and Liu. So more specifically, the bipartite f they considered is the else power of the else rooted power of this balance tree, which is a spider with s of legs having length k, and then a short leg of length 1. So this is like a pendant leaf here. So again, by rooted power, we mean that you fix those leaves and then you take L copies, glue them at the leaves, but making sure that they are internally disjoint outside the leaves. Okay, now you may feel that this tree is a little special, but it actually gives you a nice two-parameter sequence, right? Because you can change S, you can change the length K. Just by varying S and K, you get lots of different exponents. And more importantly, the work of Conlon, Yang, and Li introduced a very promising framework where subsequent work is kind of based on. So the significance of their result is really the framework they set up, the method they introduced. Okay, so then later, Yang were able to verify the Bukh-Conlon conjecture for the power of for this this spider, where if you look at their previous result, you just delete the extra leaf. Okay, so take the balanced spider. All legs have length K, you have S of them. So he showed that indeed the theorem of this is also upper bounded by what's conjectured by Bukh and Conlon, and that for large enough T, so here I mean you take T copies, glue them at the leaves, you get this new sequence of exponents. Okay, now I want to mention that the problem was really studied because it's in the language of the subdivision problem. So I don't feel that the motivation was to find more exponent, but more for resolving question on the Turán number of K subdivisions of the complete bipartite graph. So it's very nice. So he was able to completely determine the order magnitude for the K subdivision of KST. Okay, so why do I say this is tied to the subdivision problem? It's because if you look at the spider, it's just a long star, right? So if you take T many long stars, you just get a subdivision of KST, where each edge is replaced with a K-path. Okay, so this problem is actually quite difficult. Earlier, Conlon, Yang, and Li settled the K equal 2 Ks, the two subdivision, and then visiting student Yu and I established the 3-4 case, 3 subdivision, 4 subdivision. Then soon after, Yang solved the whole problem. He also introduced some very nice ideas, which led to even more work by other researchers. So yes, I want to say I feel that the work of Conlon, Yang, and Li and this work of Yang play an important role in what's to come and what will come, I think. But also I want to say that in my paper with we also introduced some new ideas which can be useful. So indeed, motivated by Yang's new ideas and plus some of our own new ideas, we were able to strengthen, kind of generalize both the Conlon, Yang, and Li result, this one, and the balanced spider to the more general setting. So we're able to show that for the rooted power of this more general looking spider, where S minus 1 of the legs has equal length K, but then you're allowed to have a short leg, and that short leg can have any length up to K. Then if you take the rooted power of this, it also satisfies the Bukh-Conlon conjecture. Okay, so what's nice about this result is now you have a 3-parameter sequence, P, K, and B. So here I wrote P. So P is really just S minus 1. Because here you see you have this, right? You can adjust how many legs. You have this, how long the most of legs are. And then this, how long the short leg can be. You can adjust all 3 parameters. So that gives you a 3-parameter sequence. Luckily, we find a very simple way of phrasing the result. So as a corollary, you can say that for all integers PQ, where Q is bigger than P squared, this exponent 1 plus P over Q is realizable. There is a bipartite graph with this Turán number. Okay, so if you phrase this way, it's quite simple. Because if you think about exponent conjecture itself, it just says for every PQ with Q bigger than P, you can realize the exponent 1 plus PQ. So we're able to say this is true if Q is bigger than P squared. Okay. Then more recently, with Zilin, Jiang, and Jie, we obtained more new exponents. It's a little technical to describe what they are. But let me tell you what the balance tree we used in the rooted power. It's a 3-parameter tree. So basically, if you think about the Kam-Kim Liu result, they have T and the first level under the center, and then S leaves under each. And then they also add S leaves to the center. So the difference here is that here we add some B leaves to the center. And this B can be quite flexible. So B is anywhere between 0 and S minus 2. As I said earlier, it may be deceptive that it's a simple modification, but it's a completely different graph because you're taking powers of this graph. It's complete different density, and you need very different arguments. So that's general. Okay, so if we can do this for every possible ST, as long as the tree is balanced, then it actually will give us a very simple sounding result. But unfortunately, we do need, in our proof method, we do need T to be sufficiently large compared to S. So that restricted the exponents we can generate. But I want to point out that one nice thing about this particular result is that in all these recent results, you do your accounting, right? You have some count of some substructure, then you do some averaging, and then you find the structure locally. So in this paper, the averaging mechanism is quite different from in the recent papers. Recent papers, usually the average is taken over some internal vertex of your copy of T, but our averaging was taken over a subset of leaves. Then we do something more. So at this point, I think any more ideas will help contributing to the problem. So in the remaining 5-10 minutes, I don't think I can discuss the proof, but I want to philosophically say what they are. I would call this some kind of reduction approach. So this applies to the results starting with Conlon, Yang, Li, and then the 3-4 results after that. It builds on the framework of Conlon, Yang, Li that was further expanded in Yang and also with my paper with you, and then with Zilin and Jie. The idea is that it kind of like in the Bukh Conlon upper bound proof, you count how many copies of T there are sharing the same leaf set. But of course, you can't guarantee that they don't overlap outside the roots, the leaves. But if you have many copies sharing the same leaf set and you don't find a clean copy, a clean power of T, then some gluing happens internally, right? So imagine you're putting lots of copies of this on the same leaves, but they are now pairwise internally disjoint, then some vertex has to repeat a lot. So let's say lots of copies glue at U, for instance. Okay, imagine you have 100 copies; they are sharing the same U. They all map to the same U. Then remember the leaves are fixed. So then you have two scenarios. Either it create lots of internally strong short paths between U and this leaf, or your U together with the other S-1 leaves form some strong, or we call strong or ample substructure, which is again some kind of rooted power of a smaller tree, subtree. And then you, well, here I'm being very vague what ample means. It's actually quite delicate. Then you count these substructures. And then the idea is that you're going to use these substructures to build your copy, okay? But unfortunately, as I said at the very beginning, philosophically, these kind of arguments would rely quite a lot on the particular structure of your graph, in this case, on T. Okay, anyways, so to wrap it up, what's next? So Bukh-Conlon conjecture is only one way to attack the exponent conjecture, but it's actually much stronger than needed, because exponent conjecture just says for any R, I can find F whose Turán is theta n to the R, okay? So no one says you have to use rooted powers of the balance tree. Furthermore, Bukh-Conlon says, not only that, but if you give me any balance tree, then the Turán has to be, well, when L is large enough, has to be a 2 minus 1 over rho, where rho is this density parameter I defined earlier. So it's really much, much stronger than what's needed. Conceivably, one can maybe come up with some clever induction where you are allowed to adjust your tree along the way. When you reduce to a smaller subtree, maybe you only care about the existence of certain subtree, right? So conceivably, there's some clever reduction mechanism that would allow you to bypass proving Bukh-Conlon, but still establish the exponent conjecture. Now, even for the Bukh-Conlon conjecture itself, which is very interesting and really very ambitious, having worked on this for a little bit, to me, I feel that it might be instructive to focus on the sparse end of the spectrum. So what I mean by that is those with Turán number really close to being linear. I feel those are the bottlenecks for a general solution. In particular, I think resolving the Bukh-Conlon conjecture for the rooted power of the following tree type would provide a lot of insight into the general problem. So the tree type is this caterpillar with very sparsely added legs. Okay, so essentially a long path, but you only infrequently add legs, one leg to the vertices. Of course, you want to make sure it's balanced. So if you just place the legs evenly spaced, it's going to be balanced. So I call this tree TSL, right? So each segment here has length L, and after every L steps, you add one leg. So if we can understand how to solve this, then I think it will provide a lot of insight to the general problem. And the reason is that for larger density, you kind of, you can think of just adding one leg to each vertex to bump up the density. And I think there is some way to reduce to this case. So that's just my personal feeling. And also for very sparse graphs, we don't have very good tools. So I think it's a nice focal point for future work. Okay, so yeah, so that's it. I usually always forget to type this. So.
Thank you, Tao. Let's try to give a round of applause to Tao, but first I need to unmute everyone, I believe. Or No, I think you can unmute yourself and try to give Tao. Thanks a lot, Tao. Any questions?
If it's not too difficult, then can you just describe very roughly how your averaging argument differs from the others? The most recent result.
Yeah, this averaging actually was kind of used in my paper with Yu on the 3-4 subdivision, but I think there's even more new ingredient to it. So if you think about your paper and also Yang's paper, let me erase. Okay, so you have lots of copies of this. And the way you averaged is you average over the center, for instance, right? So when you average over the center, you get lots of copies. So if I view these as the vertices playing the role of these leaves, so you have the central vertex, and then you have this like A1. I'm not sure whether that's your exact argument, but the gist is that you average over the center. Now you have lots of these spiders, right?
Yeah.
So if you look at the hypergraph induced on this A1 union A2 through AS, it has positive density. So then you can carefully construct the power. This is one case. Another case, if you have a lot of growing on the paths, you get lots of short paths, right?
Yeah.
And then you average over any vertex on the path. You can also say average over some center of the path. But the point of those average has the pattern that the distance from the central vertex you average over to the leaves is exactly the optimal one. You expect to hit, say, d to the m many vertices if this distance is m. So that the corresponding hypergraph has positive density, so you can do make some argument. So so in this most recent argument, as I said, in the 3-4 subdivision with you, we already has some version of that. Is you get lots of copies of this guy, right? But rather than average over center or some internal vertex, we average over this set of leaves. Okay, so the leaves which are at the bottom. So now when you do that, you can say, okay, there is this set of leaves which is hosting lots of copies of this T. But then now, of course, these vertices, say the central vertex U, and these short leaves X1 through XB are no longer fixed. So what you end up getting is you have set U of all the possible vertices playing the role of U, and you have this capital X1, capital X2, capital XB. So here, what you average over is this subset of leaves, right? So then your U and this capital X1 to XB are not fixed. Instead, you get some, you can say graph or hypergraph, depending on your perspective. Then the idea is we need to analyze what happens between inside this hypergraph. Either we can somehow build our power directly. If we fail to do so, then we can grow out and hit enough B sets, and then find a clean, careful way to glue them back. Right? So it's quite different. Do you see the difference?
Well, I'll have a look at the paper.
Yeah. I know it's technical. I mean, if you read the, I had a paper with you on the 3-4 subdivision. If you read that paper, it already has this kind of discussion.
Okay.
Yeah, the new paper has a little bit more ingredient to it.
Mm-hmm.
But I don't know. I think this approach, this kind of averaging, may be used for these caterpillars. Like you would like to maybe average over this set of legs first, and somehow allow you to extend to the next, and then you maybe average over the next set of legs. Okay, so if you grow it one by one, maybe it works for this caterpillar.
Okay, thanks.
Mm-hmm.
Any more questions? Meanwhile, I have a question. So Tao, if I understand correctly, your result where you prove things for P bigger than Q square, so does that generalize all the previous results on the subdivisions? So the one by U and Chu and then Yancer and also Conlon Yancer Lee results?
Generalize Conlon Yancer Lee and Yancer, because Conlon Yancer Lee does spider with K plus. So let me just mention what the connection is. Conlon Yancer Lee has this short leg just being a leaf. One. Yancer's result is that this last leg is full. It's also length K. So we have the flexibility of shrinking it. So yes, it covers that two sets of results. But Yancer also has a nice result on the subdivision of KT, not just KST, but the complete graph. So he has a nice result on that as well.
Okay, thank you. Any more questions? Okay, I assume not. So let's thank Tao once again for a great talk.
Thank you. Thank you for coming. Thank you. Thank you, everyone.